Quantum noise, friend or foe? IBM's latest study could change everything. For decades, the prevailing wisdom in quantum computing has been clear and a little grim. Noise, the random errors creeping into quantum systems, has been our main adversary, keeping us from unlocking the true power of quantum processors. Most experts believed that this noise so limits computation that unless we develop advanced error correction and mid-circuit measurement tools, yet quantum circuits become too fragile to be useful, collapsing into randomness after just a few steps. But what if this story is missing a crucial twist? And here's where it's about to get surprisingly controversial. A team of IBM quantum scientists has just published research that challenges this pessimistic viewpoint. They found that a certain category of noise, specifically so-called non-unital noise, may actually extend how long and how powerfully noisy quantum devices can compute. Rather than being an insurmountable barrier, noise in the right form and under specific conditions might become a tool. So what is non-unital noise? Imagine two types of random disturbance working on your quantum hardware. Unital noise, which acts like stirring cream into your coffee. Everything gets mixed so uniformly that you lose track of the original flavor. And non-unital noise, which is more like gravity tipping spilled marbles. They all reliably roll in a single direction toward the lowest point. Non-unital noise, such as amplitude damping, where qubits tend to drift into their lowest energy states, has a directional bias, unlike the all-mixing randomness of unital noise. Here's where things get really interesting. Traditional theory has mainly looked at the all-mixing unital case, assuming errors scramble information so quickly that circuits can't maintain meaningful computations. But in their recent paper, IBM researchers Oles Shtanko and Kunal Sharma showed that real-world quantum devices often experience noise with this directional, non-unital bias. And by cleverly designing their circuits, researchers can actually harness this trend instead of fighting it. And this is the part most people miss. Shtanko and Sharma adapted a concept called the quantum refrigerator, where even destructive, dissipative processes can be channeled to help clean up other parts of the system. Their approach introduces reset protocols. Think of these as a three-phase cleaning system. First, ancilla helper qubits are exposed to the noisy environment, allowing them to settle into a more pure, predictable state. Second, a special quantum compressor circuit takes the best of those ancillas and concentrates their cleanliness into a few qubits, like filtering muddy water through a series of sieves. Finally, the purified ancilla qubits are swapped into the main computation, reviving it without needing to measure the state directly, a process that's typically cumbersome and risk-prone on current hardware. This reset method sidesteps some of the thorniest challenges in quantum error correction by eliminating the need for measurements in the middle of quantum circuits. In fact, the researchers proved that with enough ancilla qubits and modestly weak but directional non-unital noise, quantum circuits could maintain useful computations to almost any depth without triggering the collapse that was long believed inevitable in noisy hardware. The technical term here is polylogarithmic overhead, meaning the increase in resource cost is very gradual even as the problem grows much larger. Could this supercharge noisy quantum devices? If correct, this finding may significantly alter how we benchmark and compare today's quantum processors. The study raises the possibility that quantum advantage, the milestone where quantum systems perform tasks too tough for classical computers, might be closer at hand than theorists expected, especially if device noise naturally has a non-unital flavor. Plus, measurement-free error correction could simplify the entire design and operation of quantum computers, since measurements remain one of the hardest things to engineer reliably. And here comes the hotly debated question. Should we rethink our whole approach to quantum hardware? Rather than fighting every bit of dissipation, maybe we should embrace and engineer around the types of noise our devices experience in nature. Could the very thing we thought was our biggest bug actually become a feature? Challenges, limits, and the big picture. Of course, the IBM team acknowledges huge hurdles remain. The error rates required for these protocols are extremely demanding, sometimes just one error in every 100,000 operations. And the number of ancilla qubits theoretically needed can be astronomical, running into the millions for practical problems. While these are worst-case theoretical figures, practical applications may find ways to optimize. Not all non-unital noise is helpful, and too much dissipation will still ruin computations. The balance is delicate. The noise must be weak, well-characterized, and harnessed correctly. Nevertheless, this discovery highlights a nuanced reality. Not all noise is created equal, and some types can be actively exploited. It also serves as a warning. Common modeling assumptions may underestimate the capabilities of real quantum hardware if they ignore the structure of native noise. The controversy doesn't stop there. Consider this. Many real-world quantum processes, like atoms exchanging energy with their environment, naturally involve non-unital noise. If simulating these is beyond the reach of classical computing, does that strengthen the unique role quantum machines could play in science and engineering? The door is open for debate. So, as you reflect on this new perspective, should scientists start designing quantum hardware that works with, rather than against, the grain of its natural noise? Or are the practical challenges still too great to justify the optimism? What's your take? Is noise still the enemy? Or the secret weapon waiting to be unlocked? Let's discuss. Where do you stand on this quantum controversy?